Thanks, Jim.
Oh, good morning, and let me cue this up. Thank you, Dr. Reddy, for the introduction. And it is always a pleasure to interact with colleagues, professionals, students at your program and across the world. So today I'm going to be presenting about diffusive gas migration through polymeric landfill covers, including those with co-extruded ethyl vinyl alcohol, polyethylene geofilms, LLDPEs, and PVC geomembranes. But I do very much need to acknowledge that over this past probably 8 years that we've been working on that, we've had many colleagues, past PhD students working with us, including Dr. Yilmaz, who is doing a visiting professor position currently at the University of Wisconsin, but recently was at Bitlis Eren University in Turkey. Dr. Benson, former dean at the College of Engineering at University of Virginia, and also Jungwon Un, an assistant professor at the University of Nebraska, Lincoln, and numerous undergraduates and other supporting students. So quite an effort over the past near decade on evaluating diffusive transport through cover systems. So just start with some perspectives. You would have to be living under a rock this century if you did not understand that greenhouse gas emissions was a world-round priority, and understanding also that many of these greenhouse gases do emanate from landfills, especially in landfills that are not properly engineered or managed. I know it's a little bit of an older reference, but the US does an inventory of greenhouse gas emissions and sinks nearly every year. And the graphic that I have up here is indicative that landfills are a large contributing source of greenhouse gases in the US and also worldwide. Well, about 55% of landfill gas can be carbon dioxide, also significant amount of methane, which is a very potent greenhouse gas. So to be part of the solution, our industry, that in environmental remediation, solid waste management, and similar, needs to be assertive and aggressive in doing our part to beneficially recover those gases that have other uses and to successfully contain and mitigate those others so that they do not become a source to our greenhouse gas emissions that the rest of the world will have to deal with. So I always do like to indicate that when we're doing our studies and research, we tend to go into a small little component somewhere in a system. And I do want to say that a municipal solid waste landfill, or any landfill in general, is a system of interrelated components. So if we are looking at, let's just say, greenhouse gas productions, that system has to consider how we handle organic waste from the community. Should that organic waste be diverted to compost centers or biodigesters? Should it even enter the landfill? What type of materials, organics in the landfill are going to be there for longer term degradation and methanegenesis, where we can recover those gases? We have to realize that landfill gas does not move quite the way that water-based liquids do, and diffusive properties very much govern how gases can escape from our system. So it is a system, and all of these parts have to come together to achieve our objectives. Now, I may be off a little bit on the, based on the size of the landfill on the SI units here, but one of our hypotheses in our research group is that if there is no landfill gas control system, no cover system, no active management, we may be releasing X petagrams of methane per year from a large system of landfills. Now, if we only put in an active landfill gas collection system, we'll easily reduce that by an order of magnitude. So let's say maybe we go to Y gigagrams of methane per year. Now, our hypothesis continues that if we put the proper co-extruded materials into a composite cover system designed within a system of a landfill gas collection and management system, we should be able to get those emissions down to Z megagrams, maybe even kilograms of methane per year on very, very well-designed and controlled system. So we have in our power as engineers and scientists a lot of power to reduce those landfill-based emissions by orders of magnitude with proper consideration and design. So I'm just going to do an example of a particular landfill that we've done some work at. Excuse me, this is the Rotefeld landfill here in Dane County. The landfill that you would see if you come to our solid waste design course in March or April of each spring. In 2017, the calculated landfill gas emissions from this Dane County landfill, 71 megatons of carbon dioxide equivalent for that methane, other compounds, carbon dioxide and nitrous oxide. This landfill is depend on volumes, is projected to last until the early 2030s, where we'll see the peak in total generated landfill gas. But it's crazy to think about this, but after this landfill is closed and many other landfills are closed, we have nearly 100 years of likely gas generation within this system that we'll have to deal with in the long term. Carbon dioxide would be a large component of that, as would methane and other non-methanogenic organic compounds such as volatile fatty acids. In the industry, we may understand and appreciate that siting new landfills or expanding existing landfills is an, I don't want to say Herculean, it can be done, but it is a long-term process. It requires good communications and with the citizenry adjacent to the landfill and your community, and major odoriferous compounds in our landfills do not help those community relations. So I started out by talking about our concerns about greenhouse gases related primarily to carbon dioxide and methane, but please realize that we have all kinds of other components in that landfill, including hydrogen sulfide, ammonia, aromatics, halogenated compounds, volatile organic compounds, volatile fatty acids that can be, let's call it putrid, to be polite, the smell, aldehydes, ketones, and other oxygenated compounds. So these are all there in minor to trace compounds. And when hydrogen sulfide just goes up to a small 0.5%, it can be quite the problem. And I hope to indicate that in a short case study that I will present before we get into the use of polymeric, multi-component polymeric geomembranes to help with our system. So the Dane County landfill built a demolition recycling facility approximately a decade ago under the goal of reducing the waste stream of recyclable or beneficially reusable components to going to that landfill. So the loads that they were accepting were wood, vinyl siding, aggregates, metal, and cardboard. Loads typically not accepted, and this primarily from contractors, building contractors, developments, and the like. Not generally accepting commercial demolition, including large quantities of crushed drywall. So maybe you might see where this is going. It was a wonderful thought to divert these recoverable units, but there is always a law of unintended consequences. So as this system operates, each of these workers, you see that they have a bin there and they are responsible for taking out wood or certain types of plastic or whatever it is. And basically the remainder of that conveyor belt after 2 loops is basically residuals from the recycling process. And you can probably see some drywall on there. Well, those residuals go to the landfill. And in early operations of this particular recycling center, all of a sudden the Dane County Health Department was getting large numbers of odor complaints at the landfill. So you can see it peaking there, where generally you might have a small number of single digits, maybe low teens of odor complaints to the health department. All of a sudden that was peaking, getting upwards of hundreds of complaints, coinciding very closely to the operations of that recycling center. What it did take is very quickly the county put in new gas wells in that adjacent to that active phase. And within a month or two, those active gas well system was able to knock down those complaints. And so we did understand that it was an issue with odoriferous compounds in the landfill. And just by the way, that is one of the gas wells that was installed. When these gas wells go in to a active phase, this gas that is collected is generally flared because it's going to have a high amount of oxygen and sucked in, because we don't have a cover system yet. So we're not controlling what goes into it. So we are removing that gas, but we are not beneficially recovering it. Without that, limits on the egress of oxygen into the waste, that gas becomes quite unuseful. So this is important because I want everybody to understand that a properly designed cover system not only keeps the bad things in the landfill, the hydrogen sulfide, the methane, the carbon dioxide, but it also keeps the atmospheric components out of the landfill because we are putting a vacuum on those wells, and we do not want to be sucking in nitrogen and oxygen, other components from the landfill. And by the way, those are participants in our short course where we get a tour. Get to any day that you get out of the office and get to go walk on the landfill is a good day, in my opinion. All right, so continuing with this case study, Dane County contracted with my research group to say, hey, we've got this issue. We have to act fast. We have to figure out where these noxious gas odors are coming from so that we can appropriately address. So we did put in a series of gas flux chambers on the an inactive part of the active phase. We designed our flux chambers after our colleagues in the industry, Reinhardt and Eklund and similar. And this is what those flux chambers look like. This is for a soil cover only, not for a geomembrane cover, but basically we just have a couple of gas steering fans so that we can distribute the gases collected into the flux chamber equally, a thermocouple so we can normalize the temperature as needed, a gas sampling port, and a pressure control port. So we were out there doing some other research, and we just repositioned our flux chambers to that active phase in the landfill. We were doing some other atmospheric modeling and had weather stations and other things. With this, we were able to see if those noxious gases were coming through the cover itself. It was an interim cover, and basically it was a silty sand interim cover. Some of it was vegetated, some was not, and this is how we can go to do active measurements. So those results over the several months that I report here, we did have them in until the freezing season. We do see and note that the y-axis is on a logarithmic scale, so it can be a little bit deceptive. But when those gas wells went in, within a week or two, our CH4 emission rates through the cover system dropped by approximately 1 order or more of magnitude. However, the hydrogen sulfide emission rate was relatively steady through the cover system. So we also were doing measurements in a grid across the cover system and doing point measurements, trying to figure out where the H2S was coming from. It was not necessarily coming through the cover system itself. And basically, here was our culprit. In the active part of the landfill, we have leachate collection pipes with that granular zone coming up, and that granular zone did not have any type of clay plug or bentonite plug. So we actually determined that much of the hydrogen sulfide that was coming from this landfill phase was coming via protrusions into the waste. So basically these aggregate leachate collection lines, the cleanouts, was the source of a lot of the, I guess I'll call it a point source of hydrogen sulfide versus the more diffuse distributed through the cover system. So in short, this is a system. We have to look at all components. In this particular case, the hydrogen sulfide came from a new stream of small sections of gypsum in the dry board that interacted in the environmental chemistry of the landfill to produce hydrogen sulfide. We had protrusions into the landfill that acted as point sources of hydrogen sulfide, and this hydrogen sulfide via some, I'm not an atmospheric scientist by any means, but my understanding is it can be transmitted for miles when we have very light, steady, calm winds at night, and that indeed was correlated to the incidences of complaints. So just a little study on the system on when we have a problem and how we can address it and look at where it might be coming from and how we can solve it. And again, this case is to just mitigate those point sources of the gas and then also put in an active landfill gas collection system. However, as I indicated earlier, there's going to be gas generated and produced at this landfill well into 21-25. And I don't know about you, Dr. Reddy or Dr. Benson. I don't think that I'm going to be around in 21-25 to see if that predicted trend of gas generation in this landfill persists. But what I want to talk to today is there a longer-term solution to managing landfill gases within an engineered municipal solid waste landfill system? I'm going to talk a little bit how the polarity of polymeric materials impacts the diffusive transport of gases through that system. And we need to realize that our decades-long use of high-density polyethylene, linear low-density polyethylene has been very good regards the hydraulic transport of liquids, fluids in general, but it may not particularly be as good or as effective or optimized for all the different types of gases that we may have in our system. So let me introduce ethylene vinyl alcohol, EVOH. It's a polymeric material. You have probably encountered it because it is widely used in the food industry to protect your Skippy peanut butter and your Heinz ketchup and other things. What this material does, it's a very thin coating of plastic that, in short, restricts oxygen into your food, thus that your food doesn't have a source of oxygen so that it can degrade. Also, it has lots of applications in fuel tanks. So nowadays, fuel tanks in most cars is a plastic variety, but that BTEX, benzene, toluene, xylene, ethylene in our gas can diffuse through certain types of plastic. So if we add a co-layer of ethylene vinyl alcohol to our gas fuel tanks, we'll keep the gas in the fuel tank and it will not diffuse through that tank. So this material can be a co-extruded material in a evolving type of geomembrane, where the EVOH is a thin layer that is sandwiched around, in this particular case, polyethylene geomembrane layers. So our industry has long used single composition geomembranes for our use, high density polyethylene, PVC, whatever the case may be. Not just my group, but other groups have been evaluating the efficacy and potential use, especially in high importance landfills that have some special issues, to more encompassing approach to keeping all of the gases contained within the system. All right. So ethylene vinyl alcohol has been hypothesized to have outstanding barrier properties to non-polar gases, such as oxygen, nitrogen, volatile compounds, and helium due to the hydroxyl groups on that polymer chain. So hopefully that makes sense. So if it has very good diffusive barrier properties to oxygen, you can see why it's being used in food containers, because they don't want oxygen coming in. But can we use that same principle to keep gases in a landfill? It's a very thin layer. It's only 40 microns thick, so it's a very thin layer, and you can barely see it in a section of a sandwich with LLDPE as the outer layer in this particular case. So our colleagues in the industry, McWaters and Rowe and their research group up in Canada and many others, have been looking at these compounds, as has our research group. So moving into the landfill containment space, can an EVOH interlayer be expected to reduce the migration of volatile organic compounds or differous compounds such as hydrogen sulfide, volatile fatty acids, greenhouse gases, and so on? This has potential use both as a landfill liner component, where long-term studies from Dr. Benson, Dr. Edel, many others in the industry have shown that the primary migration pathway in landfill liner systems is the diffusive transport of VOCs through the liner system. It's not holes in the geomembrane. It doesn't have anything to do with hydraulic connectivity. Generally, by orders of magnitude, the primary transportation mechanism of contaminants through a landfill liner system are diffusive transport of these volatile organic compounds. Also, then we will then specifically look in this remainder of presentation into the efficacy of retaining the gases within various compositions of interim landfill covers. And we are through the laboratories phase, hopefully about ready to go out into the field for some large scale tests on this. So let's get into that. Well, first, I just do want to introduce Polymers 101. As I had previously indicated, our industry has made great strides in the last 4 decades in the use of primarily polyethylene materials, generally single polymer materials, but there are other components or other types of polymers, including polyvinyl chloride and ethylene vinyl alcohol. So let me just do Polymers 101 for a couple of slides. All right, and the next several slides are from colleagues of ours that was presented at the IGS Educate the Educators workshop about 4 or 5 years ago. And these are modified and presented with permission. So a polymer is a large chain molecule with a high molecular weight, typically on the order of thousands of grams per mole. It refers to that structure that continually adds together or polymerizes the subunits of monomers. So if that repeat unit is an X, then a linear polymer would look like the lower left image, where the monomer is in a long chain, a long polymer chain. And then that single polymer change molecule, it may not be linear, but it's going to branch and bend and do things to look like it does on the right. Some of the physical chemical characteristics of these polymers that are of interest to us with respect to the diffusive transport of landfill gas is the crystallinity, tortuosity, polarity, and homogeneity. And all these physical chemical properties are going to impact the diffusive properties. So how crystalline our polymer is, those regional crystals is going to theoretically impact our diffusive properties. And that's what some of our ongoing, recently published and soon to be published papers will show. Just by the way, the length of that carbon chain is the main property that separates polymer from a normally otherwise an organic molecule. So just as an example, for carbon dioxide on the right, from research done by Copan et al. In 2010, we do see that the diffusivity of carbon dioxide decreases quite significantly as that degree of crystallinity goes up. So that's just one of those physical properties that hypothetically should impact our transport through the system. So with that background, our objectives in our research over this past years was to start with column tests to evaluate the gas diffusion in simulated covers comprised of various compositions of geomembrane overlaying a thin layer of soil. We are looking in particular on the diffusive characteristics of these co-extruded geomembranes as compared to our conventional LLDPEs and PVC geomembranes. Using this column data, we have used the finite difference method to provide solution to these diffusive cases for the estimate of gas concentration and fluxes over time. And we can then back into the diffusion coefficients for these gases of these various geomembranes and layer systems. So we've seen this before. EVOH, geomembrane, is the one that we are primarily interested in, and then a relative comparison to others. Our equipment was a column where we had very nice control on the wall. So basically it is a column that's in two halves, and then we can put that geomembrane halfway through the column, and then we get a very good seal with a PTFE gasket throughout that wall, sealed with silicone. And then we also had all of those controls and similar in the papers that we have previously published. So then in these laboratory columns, we can put the source gas in the bottom. In this case, carbon dioxide is shown. Put the geomembrane of interest and some form of cover soil, measuring then the carbon dioxide concentration in the outflow concentration. Our laboratory experiments, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different column setups, including just an aluminum plate with the sand as our control, where there should not have been any transport, and just to look at the quality control that we were able to maintain gas pressures. It didn't go anywhere, and everything was sealed as appropriate. In the laboratory, these were in hoods because of some of the gases that we were using, particularly hydrogen sulfide. So the materials are in a hood, connected with T-pipes to our gas cylinder with that regulator. And then we would take samples off the top in this particular setup, and then run gas GC, because my tongue is tied right now with chromatography for some reason. All right, so let's look at these somewhat fascinating results with on the X scale being our time. It is on a log scale, but hopefully what you see right away is that if we only have sand or silt or even clay to some degree, so we have a simple soil barrier, hydrogen sulfide, in this case, the gas that we were measuring, goes through and starts breaking through in less than 1 day. Now, I will say that these soil materials were dry on the order of only a couple of percent moisture content. So I do understand that this would be the worst case scenario because of the sand, silt, clay was more in the dry form. And if there was moisture in that pore space, that would dampen the transport. But irrespective, in the control case, what you can see is that a soil cover system essentially waves to the gases as they're going by. Interim cover soils with only sand, only silt are not very effective, particularly when they are dry. You'll see that sometimes we might use a very thin polyethylene throwaway layer to help control gases at a site. So our 0.1 milliliter polyethylene scrim layer with sand, that 0.1 millimeters does help, but basically within about 4 or 5 days, the hydrogen sulfide is transitioning right through that cover system. Same for the LLDPE, which is a thicker, more normal composition with the sand. And then finally, we see the EVOH with sand, silt, and clay being very low concentrations for upwards of hundreds of days. So in the laboratory, we show that ethylene vinyl alcohol in composite with a sand, silt, or clay is much more effective in limiting the transport of gases, in this case, hydrogen sulfide, but I also have the results for carbon dioxide and other compounds. So put it in another way, here is that relative concentration against time. This time it's not on the log scale. So we see that the PE scrim layer with silt has the highest transport of the gases. Next comes the PVC, then the LLDPE, whereas the EVOH with the silt is at very low concentration near the detection point for the full time of this experiment. So in short, an EVOH cover system can very much mitigate and control the transport of hydrogen sulfide through the cover system. Looking at breakthrough time takes a lot longer, about 22 days for the EVOH before we had measurable concentrations of hydrogen sulfide in our laboratory columns. And you also see that change in concentration with time. Now then, using that data, we can calculate the diffusion coefficients for hydrogen sulfide for conventional and co-extruded EVOH geomembranes. And we see, again, the caution that the y-axis is a log scale, but you see the 0.76 millimeter EVOH geomembrane has a very low diffusion coefficient with respect to polyethylene, linear low density polyethylene, or PVC. So the conclusions with respect to hydrogen sulfide is that we get higher relative concentrations and more rapid increases in concentrations of H2S through interim covers with thin PE sheets or conventional PVC and LLDPE geomembranes. So in short, our traditional covers are not very effective for the diffusive transport of hydrogen sulfide. breakthrough occurs at least 5 times sooner with the LLDPE compared to the EVOH. And ultimately, the hydrogen sulfide diffusion coefficient for the extruded EVOH geomembrane approximately 100 times lower than the diffusion coefficients for the PE sheets, LLDPE, and PVC geomembranes. I won't spend a huge amount of time on this, but we also have results for carbon dioxide and also for methane. So 3 of the main series that we ran were carbon dioxide, methane, and hydrogen sulfide. Same story. Carbon dioxide also goes through those thinner PE sheets much faster. Because of the particular physical properties of carbon dioxide, its size, its polarity, we do see that the EVOH in this particular case was higher than for the PVC. So EVOH is not that magic bullet for everything. It all depends on the polarity of your polymer as compared to your polarity of your gas of interest, going all the way back to like, and similar, the same thing in the mechanisms of transport. So similar fluxes for CO2, EVOH was not the best in this case because, again, we have different physical chemical properties, but it still was effective as compared to the LLDPE alone and the PE geofilm. The carbon dioxide diffusion coefficients for this study was highest for the polyethylene and lowest for the co-extruded EVOH. And if we put all of these onto a bar graph, we see for hydrogen sulfide, carbon dioxide, and methane, the relative diffusion coefficients against the PE geofilm, the LLDPE, the PVC, and the EVOH. All right, so 3 very common gases within our landfill systems: methane, carbon dioxide, hydrogen sulfide. And I guess you may ask, is it worth it to put all of this effort to keep in carbon dioxide in the landfill? Well, if we do want close to net zero landfills where we are emitting zero emissions, we do have to contain the carbon dioxide. And maybe even by keeping the carbon dioxide into the landfill cover system for a longer time, it will have time to absorb or other things that I know that Dr. Reddy and his group down at University of Illinois, Chicago are doing regards oxidation, in situ oxidation, and containment of carbon dioxide and other things in cover system. So if we put an ethylene vinyl system or other type of system in there, we keep the carbon dioxide in the landfill, we keep oxygen out of the landfill, and now we can control that methane and other gases in the landfill for beneficial reuse. That's a different type of presentation, but it's under control. So conclusions with respect to carbon dioxide, and I'm just going to read the bottom ones here. The hierarchy of CO2 in terms of highest relative concentration to the lowest was, it goes through silt, the highest, then PE, then LLDPE, then EVOH, and which was approximately the same as PVC. The carbon dioxide flux from the cover with EVOH geomembrane was 46 times lower relative to that for a conventional PE geofilm, and similar types of relative concentration and hierarchy for H2S and methane. All right, so let me just take these next 5 to 10 minutes to let you know what our lab and our collaboration is doing in my section, I guess I call What's Next Starts Now. We've been doing this for a couple of years. It's unfortunately been a little harder than we anticipated, but what we are doing is we are designing flux chambers to be able to adhere to a geomembrane in the field so that we can put flux chambers out there to evaluate very, very, very low fluxes of gases through in situ large scale systems. So we are developing a flux chamber. We have different designs, 12 inches, 18 inches, 24 inches. We are doing modeling verification with COMSOL, large scale pilot testing in our laboratory so that we can get out in the field and demonstrate these principles at field scale. So in our laboratory right now, this is our large scale prototype where we have a large air chamber where we can put in carbon dioxide, methane, or the like, assembling our environmental control systems. Right now, we're using carbon dioxide or nitrogen because those are less harmful gases in a laboratory that's not controlled. We don't have a big, large walk-in hood, I guess is what I'm saying. With then sand and a geomembrane on top, and then we can then test our flux chambers on top of the system. With our modeling via COMSOL, we have expectations about when that breakthrough time would be for various gases. So that's what we're going through right now, is this laboratory and modeling verification. So our steps is to develop a robust sampling procedure for these larger scale flux chambers, what the sampling interval is, what the sample duration needs to be, amount of material that we're removing. Are there any impacts of the flux chamber size regards to scale effects, to ultimately verify our special flux chambers for field scale evaluation. We really then want to revise our model so that we can take these laboratory results to the profession and say, hi, Mrs. Regulator, Mr. Owner, whatever the case may be, we do have evolving materials that you may want to consider in a regulatory framework, or just as a owner that's looking into the future and wants to limit their risk on gas transport to the environment around their site. So I do want to plug a few things. I want to note that Dr. Reddy, you're doing a great thing on this seminar series. My predecessors here at the University of Wisconsin started the Madison Waste Conference back in 1978, where the industry started coming to Madison. It was a long-running series. I think it went to the 23rd or 24th international version. Phil O'Leary and I are digitizing all of those waste proceedings, and we're going to be putting them on our geological engineering web page so that these proceedings are available to the public, because they're only there for print version. But there is just a lot of really great research that was done way back in the day, and we're working to get that available in archived format and distribute it to the profession so we can go back and see that these issues have evolved over the years. But it's just a great history of context on how our waste profession has moved along in the past. I do want to note that financial support for this study was provided by Coudray America, in addition to Raven Industries, who also provided the geomembranes. GCL and similar research was provided by Setco, A lot of the laboratory work was conducted first by Dr. Jungwon Un, who's now an assistant professor. I think he's up for promotion right now at the University of Nebraska-Lincoln, and Dr. Mehmet Yilmaz at Bitlis Eren University in Turkey. They were under the directions of myself and Dr. Benson. And I always will love to invite you to come up to Madison for our annual solid waste landfill design short course. Next year, it's live and in person, March 28th through the 30th, 2022. We go out to the Dane County landfill. We see all of their facilities. They have a high BTU gas plant where they're taking the methane, stripping out all of the carbon dioxide, nitrogen, VOCs, and other things, and moving that gas into pipeline grade quality, in addition to taking in a digested gas from agricultural biogas systems in the area. It's just a great plant to see how we have taken that methane in the landfill and put it to the highest possible use. So with that, I hope that was appropriate length, Dr. Reddy, and I'm happy to answer any